We have been studying vector calculus for quite some time now. We learned properties of differential operators, integrals, and we also recently seen the fundamental theorems of the vector calculus. But there comes an exciting time when we can put this into practice. We can see how all the bits of vector calculus falling together to help model and understand the fundamental properties of nature, the electric and magnetic processes. And that's where the true power of vector calculus comes clear. In particular, the two theorems, the divergence theorem and the Stokes theorem, are very useful to formulate some of the features which characterize electromagnetic phenomena, and I would like to tell you a bit more about different forms you can use to express these fundamental laws, and these are the integral and differential forms. What also is important is that you don't worry about deriving the formulas you'll see, but more importantly understand their logic. So it's not an exercise for the memory. The first law we consider is the Gauss law. It relates the electric field and the distribution of charges. So you can see that the divergence for the electric field equals to the charge density divided by a fundamental electric constant. What you can do now, you can integrate it on the left hand side and right hand side, integrate all the volume, and then apply the divergence theorem to the left hand side to express it not as the integral of the divergence but as a surface integral. And that is a very powerful result, because what you can say now that if you want to know what effect a distribution of charges has in a particular volume, you can just integrate all the surface and you will see that flux generated by that charges. So you can have a volume like in a sphere, and outside that volume you have some flux, say from some small area, which will be proportional to that value. So that's an example of a conservation, so that you make sure that you capture anything which is generated by the material inside. Another example is the law of induction. Here you connect the electric field and magnetic field, and you can say that the circulation of the electric field over the boundary of some surface is the same as the rate of change of flux of magnetic field across that surface. So here you connect the circulation of this boundary with the flux across that boundary. And what we can do here is we can change the integral form, which you can see now because you will have integrals, to the differential form. If we apply the Kevin-Stokes theorem to the left-hand side, we can write it as the curl using this theorem. And then if we compare the integrands inside these integrals, then we'll realize that they're equal if and only if then the integrands are equal, including the right sign. So we can have a differential form of the fundamental law of induction. So you can see that rate of change of magnetic field causes the curl of the electric field. So the magnetic field produces the electric field in this example. And the third example would be the Ampere-Maxwell circuitry law, which connects the magnetic field, the electric currents, and the electric field. So you can see here the circulation of the magnetic field is related to the flux of the electric current and to the rate of change of flux in the electric field. And again, applying the Kelvin-Stokes theorem to that, we can express it in the differential form, where we have the curl of the magnetic field related to the electric current density and the rate of change of the electric field, which is quite a powerful result. Now, in addition to these three laws, there is another one which tells you that there is no magnetic charges and therefore the divergence of the magnetic field is zero. And if you put these four laws together, you'll get a fundamental set of equations called the Maxwell's equations, because the James Maxwell, an Edinburgh scientist and engineer, he really was the first who realized the potential and the power of that set of equations to describe a variety of phenomena. And so here we are. These are these four fundamental equations which you, as an expert in electric and electronic engineering, are applying in daily life one way or the other. And they describe a vast majority of important applications. They describe electromagnetic waves ranging from X-ray to the visible light and radio waves. And as we speak of waves, you can indeed show that Maxwell equations can be related to the wave equation, which you might remember from the previous part of that vector calculus, when we looked at how Laplacian connects to the second derivative to give the wave equation. And the c here is the speed of the wave. And the speed of the wave here is just a ratio of 1 over square root of fundamental constants, the electric constants and magnetic constants. And this is the speed of light or any electromagnetic wave in vacuum. So you've seen how powerful is to apply the principles we learned to express electromagnetic phenomena in differential or integral forms. I would not talk more about it because the duration of this is beyond this course. But if you're curious, you can look at the additional lecture notes, which will give you a bit more background about Maxwell equations and their history. And that was the end of the vector calculus part of this course.